Okay, let's get started. Hello, everyone. Welcome to ACES introducing Intel PVC GPUs. Before we start, I want to make sure that everyone can hear me. Tanish, can you confirm that you can hear me? And also
Yes.
you can see my screen.
Yeah, I can see your screen and I can also hear you.
Okay,
I can
thank you,
hear.
Tanish. Okay, thank you.
I cannot hear
Um,
you.
okay. Hello, everyone. Welcome to ACES introducing Intel PVC GPUs. My name is Zhenhua He, and I am instructor for today's short course. And also we have Akil Dhruva, who also worked on this course materials and prepared for the course presentation slides. And also Richard will be the instructor for today's lamps, the molecular dynamics. He will demo how to use the lamps on our ACES computing clusters using Intel PVC GPUs. Here's the outline for today's short course. First, we will introducing the Intel PVCs on ACES. Um, we will briefly introduce the Intel's PVC, its architecture, and the ACES computing platform at Texas A&M High Performance Research Computing. Second, we will demonstrate how to run models of different frameworks such as PyTorch and TensorFlow with the PVC GPUs on ACES system. Here we will be using the Intel AI models. We will be running some, like, for example, ResNet 50 on ACES with the PVC GPUs. And after that, you can open the output file and see the performance of the GPUs, for example, the image throughput. The third part is about how to convert a PyTorch model to run on PVC. Here, we will show you the steps, how to convert the model, and then you will do some hands-on exercises and run your code on PVC GPU. So we have prepared some hands-on exercises for you. Similarly for TensorFlow, we will show you how to do that as well. The last section is about lamps on PVC. This will be on Richard Lawrence. He will demonstrate how to run the molecular dynamic simulations in the lamps framework with PVC GPUs on the ACES system. So the first lab is about introducing Intel PVC GPUs on ACES. And here's a picture about the Intel Data Center GPU Max Series PCIe card. We have different GPUs like 1100 and 1550. On our ACES computing platform, we have 1100 Intel Max 1100 GPU. So first, I would like to introduce our ACES computing cluster. ACES stands for Accelerating Computing for Emerging Sciences. This project is funded by NSF. The mission of this project is offer an accelerator testbed for numerical simulations and AI ML workloads. So on this ACES computing cluster, we have various type of accelerators, such as Intel PVC GPUs, Graph Core IPUs. IPU stands for Intelligence Processing Unit, and also NVIDIA GPUs and other FPGAs, for example, Intel FPGA and Beware FPGAs. We have different accelerators. We welcome different researchers in different research fields to use our accelerators to speed up your workflow. Second is to provide consulting, technical guidance, and training to researchers. We have been hosting different workshops, tutorials, and short courses like this to researchers, so they can learn from hands-on exercises to use the novel accelerators on our ACES computing platform. And also, the third mission is to collaborate on computational and data-enabled research. We have been collaborating with the different HPC centers, such as San Diego Super Computing Center and also Texas Advanced Computing Center, University of Florida, on some benchmarking projects. And also we published some papers on our results. Here is a table about the accelerators on ACES computing platform. You can also check the quantities of the different accelerators on ACES computing cluster. So we have 32 graph core IPUs, and 16 of them are Colossus IPUs, and 16 of them are Bow IPUs. Bow is a little more advanced IPUs than Colossus, so we have both. And also we have Intel FPGA, Bitware FPGA, Next Silicon coprocessors, NEC vector engines. But here we also have Intel Optane SSDs. If you have some applications that requires a large memory, these Intel Optane SSDs can be addressed as memory with the MemVerge memory machine. So we welcome you if you have any of these applications that require large memory. We would like you to test our Intel Optane SSD. So we have 18 terabyte. We have 48. So, and also we have NVIDIA H100. We have 30 of these GPUs for NVIDIA 830 GPUs. For today, we are using the Intel PVC GPUs. This is the software development platform called Intel Arctic Sound, ATSP. So we'll be using, we have 22 Intel PVC GPUs. So this is the Intel Max GPU 1100 on our ACES computing cluster. It has 1 tile per stack per card, and it has a 56 Xe HPC cores, 448 execution units. So you can calculate it has 8 units per core. The TDP, the thermal design power, is 300 watts, and we use a PCIe Gen 5 16 lanes card. And it has 48 gigabyte HBM2E memory. The memory bandwidth is 1.2 terabyte per second. The peak performance is 22 teraflops FP64 precision at this precision. So this is some specs about the GPUs. If you are interested in knowing more, and I think we have more information. There are more information on the Intel website about the Intel Max GPU series, even about the 1550. You can check that. Next, we would like to talk about the Intel One API toolkits. It's a collection of development tools that are developed by Intel. So the users can develop their high performance applications across like multiple architectures such as Intel CPUs, GPUs, and FPGAs, and etc. And also they have some add-on domain-specific toolkits. For example, Intel One API tools for HPC, Intel One API tools for IoT, and Intel One API rendering toolkits. For all of these domain-specific toolkits, we will not use them today. But if you have any interest about these toolkits, we encourage you to to look at the Intel documentation about all these toolkits so you can make use of them. For today, we're going to use this one, the Intel AI Analytics Toolkit. So we will run some machine learning models on the with this Intel AI toolkit. Any questions? I think I have. Okay. Thank you. I checking the chat message. So, to facilitate our users to use our ACES computing clusters and the accelerators, we have created some shared directories on ACES computing clusters. For example, we are save some data set for example here ImageNet data set for PyTorch and TensorFlow, and these are all processed data set, image data set. So you can directly use them with your model. If you want to train your model with the ImageNet dataset, you can directly use them. And also we have TensorFlow ImageNet dataset in TF record format. So, and also for the models, we have download the Intel AI models. So you can try out the different models. And also we have provided containers in the shared directory as well. So it's called Intel Deep Learning container, and it has been converted to Singularity image. So you can use it on our computing cluster if you are interested in. Next, I would like to introduce some of the resources we provide. The first one is our web page, TestCNM High Performance Research Computing. If you click on this link, you can see our, now I'm at the web page of our Camel HPRC. Can you still see my web browser? Give me a thumbs up if you can see my Google Chrome browser. Okay, thank you, Scott. So you can see here, we have like how to do, we have a lot of tabs here. And today we're going to use the tab to access the ACES by using Access Portal. And also you can even check the status of our computing clusters. Faster and Grace are under maintenance today, so you can see all the numbers are 0. So the next one is about ACES Quick Start Guide. If you click on it, and we have ACES Quick Start Guide here, and this is our knowledge base for the different computing clusters. You can see we also have a Faster, Grace, and Terra. So if you click on the user guide, we have ACES user guide here. You can learn about different accelerators. For example, Intel PVC GPUs here. So it will have an introduction about the Intel PVC GPUs. Our ACES computing cluster, we have 6 Slurm nodes, PVC nodes, each with the 4 Intel PVC GPUs. And how to access these GPUs by using interactive method and also the Slurm method. And also you can monitor the PVC GPU utilization by using some command, for example, sysmon, spum, CLI. I will introduce these as well in my presentation and the demos as well. So next, we will be using the ACES portal to access our ACES computing cluster. I think most of us are Access users. Here is the link to the Access documentation. Tells you how to apply an Access ID, And here's the HPRC YouTube video, YouTube channel. And we have posted, I don't know how many, 94 videos about about our short courses. You can see, for example, this is about introduction to containers, Charlie Cloud, and a hierarchical module system, introduction to Julia, and many others. So if you are interested in knowing more about Tamil HPRC and learn about our short courses, you can subscribe to our YouTube channel, and you are very welcome to look at our videos, watch our videos, and learn from our resources. Okay. This is our help desk email. You can send us email if you have any questions. So next is about how to access the ACES computing cluster. We will be using the ACES portal, which is the web-based user interface for the ACES cluster. It's based on open on demand. It's an advanced web-based graphical interface framework for HPC users. So this is the ACES open on demand portal. Next, you will do authentication via CI logon. So you can see we will choose access CI exceed, and also you will need to provide your access username and password, and then click log in. After that, I guess you will need to do the dual two-factor authentication. You will need to approve, for example, on my phone, I will have to approve it. So that's the process to get our ACES cluster. So next, we will do the click on the tab clusters, ACES shell access. We'll get on the shell. You will be able to see the login node name in the prompt. So let's do it together. So I will show it now. Please follow along, and then you will be able to work on the hands-on exercises, and then learn how to even run some demos or our with our Intel PVCs. So click on the hover your mouse over the portal tab and click on the ACES portal access. This is the access. This will direct you. So we will select the identity provider, access CI exceed, and I'll just click on log on. So I have saved my access username and password. You may need to type your username and password. So after that, I click login. Here, I will need to do the dual two-factor authentication. I will approve on my phone. So now we are on the ACES on-demand portal. So we have, you can see different tabs here. Before I continue, I would like to know if everyone is on the ACES on-demand portal now.
No.
No? Okay,
Yes.
Elizabeth.
Yes.
Well, did you encounter any error, or do you needed more time?
I needed time. I have to get to this side. I'm using another system because so that I can be looking at it. I want to know which website.
Can you repeat your question?
Is it Texas A&M High Performance Research Computing? That is what I want to know, which one to use on my.
You mean from here?
Okay.
Which one to use? We use the ACES portal.
Okay. Let me now.
Once you click on the ACES portal, as I did before, you will need to choose the access CI exceed, and then click log on, and then you will need to provide your access username and password, and then do the go through the dual two-factor authentication, and click login. It should bring you to ACES on-demand portal. And I would like to introduce the features of our ACES on-demand portal. For example, here, if you click on the Files tab, for example, this is my home directory and Scratch directory. If I click on that, you can see the files I have, and we will be downloading these. I would like to show you how to use the file editor on the portal. So when you see some files, for example, here, and you can use edit. We will do this a little later as well, because I think it's be easier for you to edit in this file editor. If you prefer use Vim, of course you can use Vim as well. And the next one is about a job, and we have active jobs, job composer. For example, when you submit a job to our ACES computing cluster, you can check the status of the job, whether it's completed or it's pending or it's running. So, and also cluster here, we will be able to start ACES shell. And also we have different interactive apps here, the VNC, and also we have Next Silicon VNC. And if you use the Jupyter Notebook, Jupyter Lab, we also have these, RStudio, TensorBoard. We also have affinity groups. You are welcome to look at our affinity groups, ACES group and our HPC group, and a dashboard. So probably this will show you some, I don't understand what's going on here. So it will show you some of the disk usage, the limit. I think it's under maintenance, maybe. It doesn't show the numbers, disk usage. So you can try out these dashboards. I think maybe this one is probably use the new one. After that, please click on the clusters and click on the ACES shell access. So we will be on the logging node of the ACES computing cluster. I'm on the logging node 1. I think we have several logging nodes.
Menu again, please. The clusters drop-down menu, please.
Cluster drop-down menu, yes.
That's the one.
Yes, this is the one you should click on, the _ ACES shell access. So you click on this will direct you to here. So now I'm on the logging node 1. So now we are all on the logging node of ACES computing cluster. So this is a success. Welcome to the ACES logging node. Next, on the logging node, we can check the PVC Slurm nodes, the status. So from here, we can view the PVC nodes and the number of GPUs. So we can use these commands. If you have the course presentation slides, you can directly copy and paste the commands into the terminal. So for example, here I will do -p. -p means partition. -g shows the number of GPUs. Now you can see we have these nodes, I guess six PVC nodes, Slurm nodes, and they are in the PVC partition. On each node, we have 4 PVC GPUs. And now their state is reserved. They have been reserved for the short course, so I reserved them. So today we are going to use all these use the PVC GPUs. Next, we will need to copy the training materials to your personal directory. First, we will cd $scratch to navigate to your personal Scratch directory. And we have saved the files for this short course at Scratch Training, ACES PVC course. So you will need to use this command, cp-r, Scratch Training, ACES PVC course, $Scratch to copy the training materials to your personal directory. And then you can enter your directory, your local copy as well. So I think I will give, I have downloaded this into my Scratch directory. So I will give you like 2 minutes to copy the training materials to your personal Scratch directory. So it should be like this. The second lab is about using PVCs on the ACES computing cluster. These are mostly demos, but you are encouraged to follow along and run the models like in PyTorch and TensorFlow framework with the Intel PVC GPUs. And also after that, after running the models, you will get an output file that shows the performance of the Intel PVC GPUs as well. So here, first, we will need to set up the environment for the first one. We will do PyTorch model. So we will need to set up the environment for PyTorch models. Here, actually, we have prepared a job file where the environment has been set up there. So we will go through line by line so you know how the environment was set up. So first, we will do module purge to clean your environment, and then we will module load the Intel AI Kit. We use this version, 2023.2.0. I think this is the latest version, but I need to check. So this is the Intel AI Toolkit. This has been installed as modules on our ACES computing cluster. So you can just simply do module load the Intel AI Kit. You can select a version, and I think we have another version as well. And then we will do module load Intel toolchain, and we will be using the 2023.07. Next, we set the variable called env_name. For this demo, we will be using the PyTorch. So we will be cloning the environment in the AI toolkit into your directory. So we make a variable named AI kit -pt, means PyTorch -GPU -clone. And if this means like if the environment doesn't exist, it will clone the environment from the AI toolkit. So conduct create -env_name, clone the AI kit -pt -GPU. So this will help you to clone the PyTorch environment from the AI toolkit. And then we can source activate the environment. This is all in the pt_demo.slurm job file. If you have copied the training materials to your personal Scratch directory, it should have been in the PyTorch folder. We will go there and look at together. So, okay, I'll go back to the terminal. And if you list and cd PyTorch, you can see the job file here. So has everyone
can you open the file in the file editor tab pane instead of the Vim?
Yes, that is also okay. If you use Vim, you can open the file from here. If you want to use our file editor, that's also okay here. I think at the beginning you should be you can under the files tab, you can click on the Scratch user and your username. If you click on this, and I believe you have copied the ACES underscore PVC underscore course here. And we have 3 subfolders. One of them is PyTorch. If you click on PyTorch, you will see some files. Ignore this one because I run this job this morning. So you can see I have some output file here. But I want you to open this Slurm job file. You can click on this button, and then you can see the edit. Click on edit. You will be able to open it from here. Oh, sorry. So the first part is about the job specifications. You are requesting, you will see the job name and the wall time is 1 hour requested, and we request 1 task. CPUs per task is 8, and we will use 1 node. The memory is 100 gigabyte, and the output file will be pp underscore demo and followed by your job ID. We will use the grass. We will request a GPU, and we want the PVC GPU and 1 PVC GPU from here, and from the partition PVC partition. Today, as I said, we will be using the reservation called training. So this is the resources that we requested. And the next part is I have explained to you about the environment setup. So, and then activate the environment. This will CD to the ResNet 50 Intel AI models, ResNet 50 folder, training. So we will run this training script. This is prepared by Intel, so we can just run it and see the performance of the Intel PVC GPUs. Okay, I will come back here. Do you have any questions so far? Can you see the file in the file editor on the Open On Demand portal? So next, we will be running, we will submit a job to the ACES computing cluster. So for example, here, sbatch, use this command sbatch, sbatch, pt underscore demo dot slurm. I'll submit job to the ACES cluster. Of course, you can use the PE stat dash p pvc ht probably, and we can do this. I will just dash in 5, maybe every 5 seconds. Access. Okay, we can see we have some students get on the using the PVC now. So let's see. Yeah, we can see we have some users using the PVC GPUs. That's great. And I think my job has been done, I guess. I can use sq-u u.zh. This is my net ID. So you can see I have no jobs running. I think my job has been finished. And the job ID is 29466. So we can go back to the file editor. I'll just refresh this page. If I open this, you can see it tells you, oh, you are using the bfloat 16 precision for training the ResNet 50, and also you are using dummy dataset for training, because I didn't specify a dataset directory. So for the ImageNet, so it's using dummy dataset. Of course, when if you want to train the model on real dataset, you can specify the path to the real dataset. And ResNet 50 training running 1 stacks bedside. Actually, this is very small because I only let it run like the first 20 iterations. So it's very fast. Uh, of course, you can let it run more epochs if you really care about the training, get a better training model. So here for demo purposes, I just let it run like 20 iterations. So you can see and all these. And also training performance, batch size, we use 256, and the throughput is 1230 images per second. So this is the output file. If you want to run more epochs longer, and you can do that after the class. In the file here, let me back to the Slurm. You can see this file. You can set the path to the data set, and also you can specify the precision that you want to run the model with, and also you can set the batch size as well. I just use some default parameters. So this is just for a demo purposes. So that's great. Some students are using the Intel PVC GPUs. That's a great start. I think let me go back to my presentation slides. Actually, I know some users, some researchers would like to prefer using the Python virtual environment. This is just for another alternative for reference. So please do not type these commands into your terminal now, because we will not show the Python virtual environment today. You can try this after the class. Actually, I have tried all these commands already, so it should work. Here, I would like to point out that if you want to install the Torch and Intel extension for PyTorch, when you use the AI toolkit, actually this has already been installed for you, so you don't have to worry about this. But if you want to install them by yourself, you have to care about the versions. So for here, for example, the Torch is 1.13, and you will have to use the matching version of Intel extension for PyTorch right now. Here, also you use 1.13. And when you want to do the distributed training, you will also need to install another library called 1CCL, Intel One API Collective Communication Library, bindings for PyTorch. Also, you need to find a version that is matching with other packages. These are all available on Intel website, and you can find the matching versions of the different packages. So if you want to try the Python virtual environment, but today we don't have time to work on these. So we changed to PyTorch directory, and then we submit the job file already. So that's great. Okay, next is about TensorFlow, but it's 51 minutes now. Probably I want to take a short break. How about we take a 7 minutes break and we come back at 11? So let's get back and at 11, and we will continue from the TensorFlow models. Hello, everyone. Welcome back. We will continue with the TensorFlow ResNet 15 model demo. Also, first thing first, we also need to set up the environment for TensorFlow models. And for here, similarly, we also use the Intel AI kit. So we just clone the environment. Why we want to do a clone of the environment? Because you have the freedom to install other packages into the environment for your own project. For example, probably you need a like TQDM or TensorBoard that that are not included in the AI Kit TF GPU, but you can, when you clone the environment, you can source activate the environment, and then you can install the module that you need for your own project. So, but for today's, I think for today's short course, we don't need a lot more, but just is for the future benefits. So, and this is also in the tf_demo.slurm. So, so we can change directory to the TensorFlow folder and then dispatch the TensorFlow demo.slurm. Let's see. So my terminal is still active. So let's see. Now I need to change to TensorFlow, and you can see the tensor_demo.slurm. So we use the command sbatch tf_demo.slurm, and you can see your job ID here, 29487. This is my job ID. And also I can, for example, watch SQ. I will try --me. Yes, Richard is working. Thank you. So you can see my job is running on AC026 PVC node in the Slurm. So it's working. And also we can watch PVC-G. So we have some users using these PVCs. So it's running. I guess this TensorFlow demo is a little longer. It takes about 5 minutes. So if you have any questions, you can let us know. Okay, we have been using, this user is using AC086. Please give a, you can hit the thumb down if you have problems running the jobs. So while it is running, I would like to go back to my slides and see what is the next. Okay, the next one is about converting your PyTorch code to run on PVC. So this is the next one, but I still want to see how many students are on the PVC now. We have a few more. Okay, while it's running, I will continue to the third lab. PyTorch on PVC. So if you have a PyTorch model, PyTorch code, how can you convert it and make it work on the Intel PVC GPUs? Here we would first we would like to introduce Intel extension for PyTorch. It's a Python package for extending the PyTorch models to run on an Intel platform like the Intel PVC GPUs. So first thing first, you will have to add the following import statement to the beginning of your script. For example, here, import Intel extension for PyTorch as IPEX. So, this is the first thing. So we will have to incorporate it to make it work on Intel PVC GPUs. It's very easy, right? The first step. And the second step is to move the model, your model and the criterion, the loss, and to the XPU. It's also easy. So you can do just your model. You have created your model and criterion, and then you just do model to XPU, criterion sim to XPU. So move it to XPU, and also after that, you will need to apply the IPEX optimize function. against the model and optimizer objects. For example, here, this is the arguments, IPEX optimize take. It will take your model and up to your optimizer. And here we use a data type bfloat 16. And actually, it also support FP32. You can try out the bfloat 16 here, and after the class, you can try the FP32 as well. Because for the next, when we do the fifth step, we will be using the bfloat 16. So they have to be consistent. For here, also the bfloat 16 will give a better throughput compared to FP32. So here we choose bfloat 16 here. The first step is move the data and target to XPU. Very similar in other like a GPU code. In the training loop, you have to data, when you unpack your train data loader, you have the data to XPU, target to XPU. So these are very simple change. As I said, the fifth step, we will use the auto mixed precision here with the bfloat 16 data type. We will use this context manager torch XPU AMP.AutoCast. It accept the arguments enabled to and a data type to be consistent with the previous one. So torch bfloat 16. This is all the steps. So this is just a few lines of change in your code, and it will be able to run on the Intel PVCs. Here I have prepared exercise file called a cipher10 underscore PVC underscore todo.py. I have listed these several steps in the to-do file. So you can use our file editor of the Open On Demand portal. You can add all these changes to the file and read through the code and familiarize yourself with how to change the code, the PyTorch code to PVC code. And after completing all the to-dos in the cipher10 PVC to-do file, you can modify the Slurm file and submit the job. For example, you can just aspect, you will have to change the Python command. For example, Python, you want to change the file name to be cipher10 underscore PVC underscore todo.py. Okay, let me show you here. I will go back to my PyTorch folder. So go to the exercises folder, exercises. Here, you can see the to-do file here, cipher10 underscore PVC underscore. You can use of course, you can use our file editor here. I just closed too many. File editor has been, this is for the PyTorch. And click on the exercise folder. And we have this to-do file. You can click on this and then edit. So you can see step 1, import the package of Intel extension for PyTorch and give it an alias, IPEX. Write your code below. So you can see import fixme. You will have to replace fixme with the correct code as shown in the slides. So this is the first step. And after that, you can read the code through. And then in second step, move the model and the criterion to XPU. So now we have our model and the criterion. In the second step, you will need to do model equals model.to and then XPU and the criterion XPU. So you will have to replace the fixme with the correct code. So this will be the several steps, you change it to a PVC code. If I go back, you can see we have a solution, but I don't encourage you to look at the solution now. I want you to first complete the exercises first by yourself and then submit it to our computing cluster. And also, we have another file called cipher10 underscore CPU. This doesn't have the model to XPU and all these lines, or I just commented all these lines. So the PyTorch model will run on a CPU. It will take a long time. I don't encourage you to run this file during this class. If you have interest, you can run it after the class. So it takes several hours, but for the PVC, it could just a few minutes. So we just want you to feel the speed up by using the Intel PVC GPUs. So now I will go back to this slide. So I will give you like 10 to 15 minutes to work on these exercises, to complete the to-do steps in this cipher10 underscore PVC underscore to-do. After that, you can submit the job. I have prepared the solution. I always want to use the Beam, but I think I want to advertise our file editor here. So you can see this is the solution, and the code changes are like you import the Intel extension for PyTorch, and also you move the model and the criterion to XPU, and we use the IPEX optimize, and you take the model optimizer and the data type. And for here, in the training loop, we move the data and target to XPU. And also we use this Torch SPU AMP AutoCast contents manager, and then to wrap it. So this is just a few steps. So you're welcome to try it on your own code. Okay, I guess we will continue. TensorFlow on PVC. So TensorFlow on PVC, it also has a corresponding package called Intel extension for TensorFlow. For PyTorch, we have Intel extension for PyTorch. It's also this package enable your TensorFlow model to run on Intel XPU like GPU, CPU, etc. And also here you can check the version, of course, using double underscore version, and to print the version you used. Good thing is that if you install Intel extension for PyTorch in your environment, the default device will be the Intel GPU. For example, if you have the Intel PVC in your, if you installed this package in your environment, it will automatically use the Intel PVC GPU. You don't have to do any code changes. So that is a great news, right? That's a great news for TensorFlow. So if you use TensorFlow, you just need to install the Intel extension for TensorFlow into your environment, and then you don't have to make any code changes. It will pick up the Intel PVC GPUs and run your model on the with it. So this is a great news. This is for great news for the TensorFlow users. Here is a very simple exercise. You don't have to change anything. You just needed to actually modify the Slurm job file tf underscore cipher10 underscore pvc.slurm and submit your job. You can see it runs on the PVC already. So this is a screenshot of the job file. You can uncomment these two lines and to let it run on the PVCs. So let me go there and try that. This is what is a change tensor flow, and I guess it's in the exercises. So we have the Slurm file here. I'll just use BAME. So you can see, please uncomment these two lines. Oh, yes, and then submit this file. I have a job ID number 29502. I'll just watch SQ dash me. It's pending now. Request node not available. Maybe. Let me see what's happened there. Okay. Because all the nodes have been reserved. So if you do not put the reservation, your node will not be able to find it. So let's add this SBatch directive here. -- reservation equal training. So let's add this line and try that again. So because it cannot find a node it can use. So now I have the new job here. So because it's in I specified to use the reservation, so he can find it, and I'm using the AC086. It's running. So it's just a line of code. I will check. You can also check the PVC dash G. Oh, what that page? Oh, okay. Just so we have some users using these PVCs. That's great news. And I'm myself is using the AC086. Seemingly, I'm very alone on this node. I need somebody to get on this node as well. So, okay. This is very easy, and I would like to actually look at the file. So you can see actually we have imported the Intel extension for TensorFlow, but actually it doesn't have any of these it doesn't use the I tags at all. So I think if you have the Intel extension for TensorFlow installed, you don't even have to put this line of code to it. Let me try. I'm very curious about this. If I do not use these two lines, can it still be landing on the PVC nodes, or it will give me some? First, let me see. Let me SBatch TF underscore. Okay, commit. SBatch. Where's the S code? So 29507. I will just watch SQ dash me. So it's also running on AC086. How can I check if it's really using the PVC GPUs? We want you to always follow the good practice, and we want you to probably when you run these, you want to use the VNC for checking the PVC usage. I will introduce it a little later, but we can see actually it's landing on the PVC node. Do you have any questions so far for the TensorFlow? TensorFlow is an easy one, right? So you don't have to do any code changes. Okay, I think I will move on. We have some PVC monitoring tools. I just introduced the PE-stat-P partition, PVC-G, to show the number of GPUs. And this is one, you can use this one to check the availability of the PVC GPUs. And also, actually, we can monitor the PVC system activity, use the sysmon. It will tell you the memory being used on the PVC and other information as well. Another one is to use the Intel XPU Manager. It's a XPU M Manager CLI command. You can use the stats -d, and you can give it a device index. For example, you use 0, and you can give it 0, and you will be able to show the memory used and GPU utilization. Oh, because sysmon, if you just use it now, I guess it's not on the, you are on the login node now, so it's not on the PVC node. So sysmon error it's expected. So only if you get on a PVC node, you can use this sysmon. Here is how we can directly land on a PVC node. For example, we can use the VNC. You can start a VNC. I have introduced about the interactive apps. So you can click on VNC, choose the node type, for example, Intel GPU Max, and the number of GPUs. For example, here I choose 1. If you have a distributed training, you can choose more. And for example, 2, 3, or 4, and the number of hours, number of cores, total memory. And after that, you will be you will after a short wait, you will be able to see this blue button called Launch VNC. Click on the Launch VNC, will bring you here. For example, in the VNC, we can run some jobs. I don't know why I just covered my username, so I think that's okay. And then here I change directory to the PyTorch ACES folder, and I do some module load of the Intel AI toolkit, and also module load of the Intel toolchain. I also activate our Colonial environment called AI Kit PT GPU dash clone. And here on this node, I run this CIFAR10 PVC solution file. And after that, you can use watch sysmon to see the memory usage. And this shows your process is attached to this GPU. This is a good practice to check the PVC memory usage. And but if you want to check the power and temperature of the GPU, you probably want to run the command xpu mcli stats-d device. But for today, I guess I will just show these. I did this before I think it was yesterday. Yes, it was yesterday. I tested, and you can also use our VNC session to check the PVC usage. I think that's all for the AI ML part in PyTorch and TensorFlow. Next, I would like to invite my colleague Richard Lawrence to do some to show some demonstration and maybe exercises on running LAMMPS, the molecular dynamics simulation on PVC GPUs. Richard, are you there?
Hi, this is Richard. I'm a user support specialist at Texas A&M, and I will be talking to you about running lamps on PVC GPUs. I hope you can see my screen. It should look pretty much the same as the other one. So, what is lamps? Has anyone heard of lamps before? Lamps is a molecular dynamics simulation engine, and lamps has a modular backend for GPU acceleration. So there are two main lamps packages that serve that purpose. The GPU package uses OpenCL or CUDA to communicate with GPUs, and this package divides work among the GPU and the CPUs. There's also the COCOS package, which uses a different type of declaration language entirely, and that supports many more types of accelerators, including different types of CPUs. The default strategy, if you're using a GPU with the COCOS package, is to put every calculation on the GPU. I've used both of these. They do both work well. Today, we will be focusing on the GPU package, which divides work among the GPU and the CPUs. For other purposes, the COCOS package may be better. I just don't have an example prepared. What's different between these two is primarily there's a slight change of syntax when you launch your executable, depending on which package you're using to communicate with the GPUs. Mostly, your input files are not going to vary very much. LAMPS is pretty good about behaving as though this is a modular backend. So ACES, we provide a build of lamps that's compatible with the Intel GPUs, and I have put it in a module. So that is the lamps module, which has the version named 3 August 2023-Intel-2023.07. So here the first phrase, 3 August 2023, refers to the build of lamps itself. So that is a release of lamps from that time. And the second phrase, Intel 2023.07, refers to the version of the Intel compilers that were used to compile the lamps code into executables. And because the module system on ACES is hierarchical, you must load your toolchain before you load your application. So the syntax is module load Intel 2023.07, then module load lamps 3 August 2023-Intel 2023.07. However, because there are only a few things available on ACES that are specific to this toolchain, it's actually good enough to just say module load Intel 2023.07 lamps, and there's only one reasonable option that the module system can consider, so it picks the right one. So it saves you a few keystrokes. Where is this installed? When you load the module, it sets an environment variable named HPRC root lamps, which just points to the directory where this build is installed. So we can take a look at it and see where it is. You could consider this to be a small exercise if you wish. Module load Intel 2023.07 lamps. Echo HPRC root lamps, and it is located in HPRC's software build directory under a folder with the same name as the module. This particular build of lamps provides an executable named, sorry, it's hard to see on my screen. I'm trying to type an underscore, but it's kind of invisible. Don't know what happened. So this particular build of lamps provides an executable named LMP_1API, if you recall, one API is Intel's name for the collection of compilers that are meant to be used across multiple types of devices. It is common practice in the LAMPS community to name your executable after the type of devices it is meant to be used with. So for example, you might see LMP underscore MPI, or you might see LMP underscore CUDA. These types of things are common. So NVIDIA has followed that paradigm, and they've decided that this executable will be named LMP underscore 1MPI. Otherwise, other than the name change, it functions identically to all those other LAMPS executables you may have seen. So because I said that this build of LAMPS distributes work between the CPUs and the GPUs, that means we will be using MPI as the layer for communicating among the CPUs. I've discovered that MPI doesn't play so well with srun. It might be a bug, or maybe I just don't understand how srun works. But in order to get the correct performance, we're going to be using sbatch. So sbatch file name, and somewhere in the file, there's your MPI run command. So the syntax for MPI run is -np for a number of processes, and then n here represents any variable number of processes. For the MPI thread configuration, we have here some suggested variables. I don't know what all of these do because I'm not actually an MPI expert. I got these from our Intel representative who suggested these. So we're going to try them for this demo. It is not known to me if there is a better combination for your specific use case. One final new thing is called the compute aggregation layer. This is a tool that Intel released, which is it's a helper for when you are running applications that use both MPI and OpenCL. So for example, the LAMPS GPU package that we're using today is an example that uses both MPI and OpenCL. So naively, if you MPI run a bunch of processes, then every process can send OpenCL calls to any of those GPUs. That might result in communication bottlenecks or other inefficiencies. So CAL, the compute aggregation layer, works as a middleman between your MPI processes and your OpenCL devices. It collects incoming OpenCL calls from the MPI processes and more intelligently handles them out to the OpenCL devices to reduce communication bottlenecks that could occur due to the MPI processes not respecting each other very well, so to speak. Now, the utility of this, of course, entirely depends on how much work Intel puts into making sure that it makes good choices. I'm not really an expert on that. I just know that we're going to be using it today because it is essentially recommended by Intel. So let's give it a try. In order to use cal run, you just prepend your MPI run with the cal run executable that sets up an environment so that it's going to intercept those calls from MPI processes and redistribute them to the GPUs intelligently. Cal run executable is provided with the LAMPS module, so you do not need to load any additional modules. It is already in that same installation area. In order to benchmark LAMPS, we have some test files that were provided by Intel. So these are Intel's variant of common molecular system input files for LAMPS. I know what some of these are. For example, on the bottom left, we have LJ, that stands for Leonard Jones, which is basically the billiard balls model. The atoms can bounce off of each other when they are in close contact, and that's it. And on the top right, we have Rhodo, which is short for rhodopsin. Rhodopsin is a protein that is solvated in a bilipid layer with ions. It's just about as complicated of a molecular system as you can design. So we run the full gamut here of very simple to very complex, and you can try any of these out. The default one is LC. It's actually one I don't know much about, but we can mix and match for fun. So try any of these that you think are relevant to you. The test files are found in HPRC root lamps/apps/capital-test. So let's navigate to that directory and see what's there. Yep, those files are there. I'll actually return to the previous. Oh, I was in my home directory, so I guess that's not very helpful. Okay, so I have provided a demo Slurm batch file, which probably should be in the directory that you already copied. So earlier we made a copy of the ACES PVC course, and one of the 3 directories in it is named lamps. And in that lamps directory, there's just this file, the lampsdemo.slurm. So let's take a look at what's in this file. So I here have my ACES file navigator open, and I have navigated to the ACES PVC course/lamps directory, and in it you can see the lampsdemo.slurm file. So I'll just click the view button to open this in a tab so we can read it and go over what is in here. So these top few lines are normal looking Slurm parameters. Things like we want to be on one node, we need some memory, we need some time. And in this demo, I've picked 1 GPU and 16 cores. So as your exercise, you may choose to vary these. Recall I said that the LAMPS GPU package will distribute work among the GPUs and the CPUs. So as you vary these numbers, you will see varying performances. Here's some printing out some fun facts about the node that your job will land on. I find handy. Here's where we load those modules, load Intel 2023-07, load LAMPS 3 August 2023, Intel 2023-07. I create a variable for the output because LAMPS does produce a log. So we'll just have a log directory and create it to make sure that it exists. Here's the MPI communication settings I previously told you that were suggested by Intel. I don't have a reason to change these, so I've just put them here. If you're an MPI expert, you might choose to play with those and see what happens. Next, we need to navigate to the directory where those input files are located in order to use them. This CD will happen in the running job, though. This will not happen in your command line. In your command line, you'll simply be located in the folder where the Slurm file is. And then I've created a variable named in, which I just choose to be one of the input files that is located here in the test directory. So this default that I picked for you is LC. Perhaps we might be interested in what is LC. I don't know. It says it's biaxial ellipsoid mesogens in isotropic phase. I know what the word phase means. The rest of that is a mystery to me. What were we doing? We were reading this file. Okay, so let's read these LAMPS arguments. If you're not familiar with molecular dynamics, I can give you a real quick rundown on what these options do. The first option is obvious. -in just tells which input file we will read. -v is, it sets a variable. The variable's name is capital N. The Intel input files all have this variable defined, which turns on and off the Newton parameter of molecular dynamics. So in molecular dynamics, you have to say you're computing the forces on 100 atoms. So first you'll compute the force on atom number 1 due to atom number 99. And then at a later time, you compute the force on atom number 99 due to atom number 1. If you're in serial or in a shared memory environment, you might notice that those are actually the same magnitude. So if you record the magnitude the first time you calculate it, then the second time you need to calculate it, you can just read it out of memory and save time. But we are not in a shared memory environment. We are distributing work across multiple devices, including GPUs and CPUs. So reading the result of the force calculation from the previous time that it was done isn't actually faster, it's actually slower. It is faster to simply recompute the force a second time. So we turn off Newton's third law here and we say, we're not going to assume that the force on A is the same as the force from A because it's faster to just recalculate. So off. PK is which package we're using for our to access GPUs. We're using the GPU package, not the Cocos package. If you were using the Cocos package, then this would be KK for Cocos. And then there's an additional argument when you use the GPU package, which is how many GPUs. So because we previously defined how many GPUs up here with the GRES parameter, instead of writing that number down again, I'm going to read it out of Slurm using the Slurm variable, Slurm GPUs on node. That way, if you decide to change this number up here, LAMPS will get the updated number of GPUs that are assigned to this job. Then we have the flag SF GPU, which means that we're going to be assigning force calculations to the GPU. I believe that's what that means. So some amount of work will be assigned to the GPU, and the other calculations will be done on the CPUs. LAMPS will output two different ways. It will either output to a log file or it will output to the screen. We don't need both of them, so we're turning off one of them. We're going to set the other one to the output file in an output directory we previously made. And for the special case of rhodopsin, there's an additional parameter named D, which has to do with diffusion, and we're just making sure that it's set to 0, and I don't even know what it does. Sorry about that. So the last part of the job is we have to put all that together. We have to say we're going to do a cal run, NPI run, number of processes equal to the number of tasks that we requested up here. So every core gets assigned one MPI task. LMP underscore one MPI, and then all those arguments that we saved. So that's what this file does. Are there any questions about what's in this file? Or would you like some time to edit the file? Otherwise, the next thing we're going to do is submit the file to the batch system and see what it does. Because I did not put the reservation flag in the batch file, if you wish to use the reservation, you will be providing the reservation flag on the command line instead. So it's sbatch -- reservation equals training space the name of the Slurm file. How much faster with Newton's third law off? I don't know for every case whether it's much faster or not with Newton's third law off. That's one of those things where you would need to do the experiment to find out. It's off because, at least in theory, it's better to be off when you're using GPUs. But whether it's actually better, you would have to try it and find out. In my experience, it depends on what kind of system. Some systems don't have a lot of force calculations. For example, the Lennard-Jones, the billiard balls model, there are very few force calculations. So saving time on a handful of force calculations doesn't really matter. But then you have like electrostatic models like EAM, the embedded atom model, where there are a lot of force calculations. So having Newton's third law matters more for those cases. And no, I don't know all of them. I'm not really a chemist. I just know how to push the button that makes it go. How many GPUs per node? Are they all in use? We can double check PE stat PVC, capital G. So we have here several nodes that are reserved today. Each one has 4 PVCs on a node. So you can request a number of PVCs from 1 to 4 for this experiment. The default in the file was 4. Was 1, but you can change that. Can lamps use different GPUs on the same node for distinct MPI ranks? In theory, yes. However, because we're using cal run as the integration layer between MPI and the GPUs, we are not really in control of that. Instead, we're deferring to Intel on their expertise for the best use of MPI with their GPUs. If you didn't use cal run, you could manually specify how your MPI ranks are getting assigned to GPUs. In the case of, for example, the COCOS package, where all of the work is going to be moved onto the GPUs, it is better to have just one MPI rank per GPU, so they're not competing with each other for access to the GPUs. For the GPU package where work is being divided among the GPUs and the CPUs, it's more complicated, and in general, I don't know the answer. Someone is pinging me. Oh, that's unrelated. What were we about to do? I forgot already. Thank you, Carl, for your good questions. I'm sorry I don't know. 16 ranks, they are in parallel. So MPI run launches the 16 processes together. We can explore that. As we submit some jobs. Do we have time? I think we do, yes. So we'll explore that, Carl, after we submit some jobs. So I just need to go to my directory where I have these files. Does everyone have a directory like this with this file? So I'm going to do sbatch -- reservation equals training lampsdemo.slurm. There is an underscore in the file name, just for some reason it's not showing on my screen, and I don't know why. Yeah, I don't know, that's weird. So I submitted batch job 29518. So I have been assigned to node AC026, and my job is running. So AC026 PSUX. Oh, looks like I'm too late. Yep, the job is already done. If we want to catch it in action, we'll have to make it run for longer. So let's take a look at the output. So we get 2 outputs here. We have a lampsdemo.job ID number, which just has a handful of statements explaining what was run. I always like to print out these statements because if I come back later and I forget what I was doing, it can be very hard to figure out what I was doing. So here we have a record now that this job ran on AC26, and we had 16 processes, and the log file went here. So we could take a look at that log file. If you know how to read LAMP's log files, this particular problem statement had 32,000 atoms, and the 16 MPI processes were divided into a 4x2x2 grid of MPI processes. Then, because there's a replicate statement, the system is replicated 16 times up to 500,000 atoms. That's standard practice for lamps benchmarking. We can scroll down a bit and you can see that here there is one GPU device that was initialized. It happens to be the device numbered 0. If we scroll down a bit more, you can see that the 16 MPI processes are all able to see device 0. If we scroll down some more, we can see that the performance over, this was the warm-up 10 steps. If we scroll down some more, you can see that for the 840 steps after the warm-up 10 steps, the performance was 41 million atom time steps per second. That's a standard unit of performance for lamps benchmarks. We can see that this one spent most of its time doing pair calculations and other, which probably has to do with waiting for communication between the devices. The total wall time was only 19 seconds, which is why I didn't catch it live. We can try again, and I'll try to catch it live. SBatch, SQ, same node. There we go. So if I hit it with PS while it's running, you can see that there are many, many copies of LMP1 API. That's because the MPI run launches many copies of the executable. And it's the job of MPI and Cal to make sure that all these processes are talking to each other correctly. I believe that means we have enough time to try some experiments. So is there another combination you would like to try? Perhaps a different resource count, more GPUs, perhaps a different molecular system, one besides the LC. I don't have a specific exercise, except we can make some changes to this demo file and see how the result is different. Is there an optimization command we could test? What were the choices again? Let's review the choices. Oops. So if we look here at our lamps demo.slurm, let's suppose I go to edit the file. The first few parameters are requesting resources. So one option we could do is we could change what resources we request. We could request a different number of PVC GPUs, any number from 1 to 4. I don't have a multi-node example set up, so we'll have to be on a single node. We could also change the number of tasks from 1 to, I think, definitely 64 is fine. I don't remember how many cores are on the node. Is there 96 cores on a node? Does anybody know? But I've tested up to 64 and it worked fine. And then the other option was we could pick a different input file. So here we picked LC. We could pick one of these other ones instead. Iribo, DPD, EAM, LJ, Roto, Snap, SW, Tursoft, Water. Can you specify which GPU to use instead of lamps pick automatically? Because the GPUs are allocated by Slurm, it's not a good idea to try to manually pick a GPU, because if Slurm gives you a different GPU than the one you hard code into your file, your process won't be able to launch at all. Generally, we let lamps pick the GPUs, but to illustrate what I mean, why don't we just change this number from 1 to something else? For example, we could change it from 1 to 3. So if I click save here, now if I launch that, it's going to try to use 3 GPUs. And we can see how the output is different. Which choice has the most atoms? I don't know which choice has the most atoms. If I had to guess, I would say they all have about the same number of atoms. The standard practice is to pick a system and then replicate it up to a specific size. So for crystals that only have like 1 atom per unit cell, we replicate it 500,000 times. But for something like rhodopsin, you don't replicate it at all, Instead, you just add water molecules until you get to the target atom count. That's a standard practice in the LAMPS community. But I don't know for a fact how many atoms are in each of these files. I didn't explore all of them. So if we look in the logs, we can see there's now a log file for the job that ends in 23. So if we explore that, we can see what's different. Same number of atoms, but now it says that it found 3 devices numbered 0, 1, and 2. It did not find device number 3. That's because Slurm arbitrarily picked for this job to have device 0, 1, and 2 and to not have device 3. Next, we can see that it initialized devices 0 to 2 on core 0. That means all 3 of the GPUs are visible to core 0. All 3 of the GPUs are visible to core 1. If this was all there was to the story, you'd have a huge communication bottleneck as every core tries to talk to every GPU. So hopefully something is going to stop that from crashing your system. And I believe the meaning of it is that CalRun is going to stop that from crashing the system, because CalRun is going to intercept all of the OpenCL calls from the cores and redistribute them among the GPUs intelligently, so we don't have that bottleneck. We can see that the performance increased from 41 to 49 million atom time steps per second. So with 3 times as many GPUs, it took a little bit less time. The communication time increased dramatically. It used to be mostly pair and other. Now the communication time and the modified times are more significant. So what that's telling me is that the additional work done by the additional GPUs was kind of negated by the additional communication time that was needed to get those GPUs to work with each other. These are the kinds of things you need to be aware of when you have lots of choices of ways to divide work among devices. The wall time was overall less, but not by a lot. With nodes equals 1, you're limited to tasks equals cores. Tasks equals cores is just one way to ask Slurm for cores. You can also ask for CPUs per task. You can also ask for all the cores on the machine. And a number of tasks is just my favorite way to request cores. There is more than one way in Slurm to specify your resource that you need. Usually they're equivalent. LAMPS, for example, doesn't care about the distinction between a task, a process, or a thread. It will just launch processes and assign them to cores as best it can. But there are other applications where the distinction between a task and a thread actually matters, but not for LAMPS specifically. If you request n tasks equals number of cores plus 1, I don't know what happens if you request contradictory resource requirements from Slurm. I'm guessing that it has some kind of internal tiebreaker and it just ignores the parameter that it doesn't understand. Also, you have to be careful because some of the Slurm parameters describe the node you want to land on, and some of the Slurm parameters describe the resources that you need. So you could say, I want to be on a node that has 96 cores, but I only want to use 2 of them. That's something you can do in Slurm. So you can't just assume that all of the parameters get you what you need. That's why I try to stick with just using n tasks, because I understand what it does. So I don't have to worry about Slurm jobs that don't work properly. You could increase the nodes tasks and see what would be the performance boost. Yun Shen would like to know what happens if we vary the number of tasks. Would you like to suggest a different number of tasks than 16? Perhaps double to 32. Shall we double to 32 and see what happens? Do you want me to put the number of GPUs back to 1 or leave it at 3? GPUs back to 1. Okay. So I clicked save. The button changes to darker color after it's saved. And then we can submit that demo again. And it is running on ACES 026. All my jobs are landing on ACES 026 today. Okay, and it is done. So now we can investigate the log for the job that ends in 25 and see how it's different. You can see that it initialized more processes and the number of atom time steps per second actually decreased. So it used to be 41 million atom time steps per second, and now is 31. There's a couple possible explanations. One is there weren't enough atoms in this benchmark to keep 32 cores busy. If you initialize more cores but don't give them any work to do, you're just essentially wasting time initializing cores. So in order to put 32 cores to work, maybe we needed to have more atoms. That's one possible explanation. Another possible explanation is maybe the GPU is getting hot because I used it repeatedly. You can see I keep landing on device 0 on node AC26. So it's possible that the node just is too warm now. But I haven't really gone into detail about measuring the temperatures. Carl asks, could you re-elaborate more on why the comms overhead is so much greater with 3 versus 1 GPUs? I'm not a lamps expert. I just know how to push the button to make it go. But my experience with lamps is that you want to give every device that's going to do calculations enough atoms that it's going to be busy doing calculations for a while, because communication between devices tends to be the slowest part of simulations. So if you give a CPU or a GPU like 10 atoms and then immediately say, hey, give me the results back, you're spending too much time communicating. You're going to bottleneck your simulation on communication. You want to give each device like 1 million atoms so they can all do their thing for a while, and that dilutes the effect of communication as the bottleneck of your system. Are the GPUs loaded sequentially? I do not know. I do know that the atoms are divided among the GPUs according to a approximately spatial partition. Lamps divides the space of your simulation into chunks and assigns a bunch of neighboring atoms to the same device. So if the atoms need to talk to atoms that are in a different partition of the simulation, then the 2 GPUs that are in charge of those atoms need to communicate with each other. Communication between GPUs is not as fast as the GPU doing its own work. So the more you partition your system, the greater the surface area between the partitions, the more communication has to occur. So with the same number of atoms and you add more GPUs, you're increasing the average amount of communication that needs to occur. So if the GPUs aren't doing enough work to make it worth that added computation, then you don't see any performance benefit. That's why it's important to know the size of your system so that you know that each device is getting allocated an adequate number of atoms to keep it busy, so you don't have to think as much about that communication bottleneck. That's not specific to Intel or GPUs. That's really just a lamps thing. In other simulation frameworks, there are other considerations. Thank you for your good questions. You've pretty much reached the end of my knowledge about lamps. I'm not a chemist. So if you have more questions about lamps, it might be better to go to the lamps community and ask them what they think. With no more questions, that brings us to the end of our course. I would like to share with you our acknowledgement slide. This work was supported by the National Science Foundation So here are some awards. Obviously, the ACES award, which paid for the accelerator test bed that we've been using. But also we have some other NSF awards. We have the Sweeter Award, Southwest Expertise in Expanding Training, Education, and Research. Sweeter pays for some of the development work for the educational materials and things like user support. If people need to travel to group meetings to collaborate on these user trainings, if they're in person, Sweeter does those kinds of things within Texas and a few neighboring states specifically. Then we have the NSF Award for FASTER, which FASTER is the flagship. Let's say flagship. It is a production cluster that focuses on composable nodes. And a lot of what we know about running code like AI and LAMPS, we learned from when we were doing those tasks on the FASTER cluster. So when I say things like, in my experience, you need to assign enough atoms to each device to keep it busy. That experience comes from the time that I spent working with the FASTER cluster. So that means that award did in some way contribute to this training. We have an Intel representative, Duni Aribuki from Intel, who provided us with the software build capabilities for the AI and the LAMPS technologies that we explored today. And also, I would like to thank the staff and students at Texas A&M HPRC, without whom training sessions like this wouldn't be possible. It takes a lot of people to keep a cluster running and make sure everybody has access to it in time to do your exercises. I think that's the last slide. No, it's not the last slide. So here's our HPRC help desk's email, help@hprc.tamu.edu. That's how you contact us. If you have questions, if your job's not running, you just please do tell us the basic information, like what cluster you're running on and your username, and we would like to help you solve your problems. Okay, that really is the last slide in the slide deck. I guess I should ask my colleague, Genoa, if he wanted to add anything else before we dismiss the class.
No, thank you, Richard. And I really want to thank everybody who has attended our short course introducing Intel PVC GPUs. We also welcome collaborations on like benchmarking our accelerators such as Intel PVCs. And also, we have various types of accelerators. If you have like you want to speed up your science with any type of the accelerators available on ACES clusters, you're welcome to contact us. And we are here to help you and also help us ourselves as well. Thank you. Thank you for joining for today's short course. Thank you very much.